Patch needs to pick up a prescription. His phone says the pharmacy is 400 meters away. Split the street in two. On the left, the green pharmacy sign sits at the end of a continuous sidewalk. Patch walks forward, crosses at the corner, and follows the shade to the front door. On the right, the same sign is visible across 6 lanes of traffic. The sidewalk bends into a parking entrance. The nearest marked crossing sits further down the block. The shade ends at the curb. Zoom the map out and the trips look almost identical. At eye level, one route keeps showing Patch a clear next move, the other keeps interrupting it. We often talk as if perception happens first. You see the street, understand it, make a decision, and finally tell your body what to do. Your nervous system, however, does not wait for those steps to finish in sequence. From the moment a space comes into view, it is already being related to your body and your possible movements. Psychologists call these possibilities affordances. A bench affords sitting, an opening affords passage, a curb may afford a step for one person and present a barrier to another. The affordance belongs to the relationship among the environment, the body, the person's abilities, and the current goal. In 2019, Sakira Jibera and colleagues tested this idea using virtual architecture and mobile EEG. Participants stood in one virtual room facing an opening into another. The opening was either 20 centimeters wide, 1 meter wide, or 1.5 meters wide. They saw the opening before they knew whether they would be told to move through it. That separation let the researchers examine the first response to the space before the movement instruction arrived. Within the first 0.2 of a second, the impassable opening produced a different pattern of early cortical potentials from the 2 passable openings. Later, when participants were told to move, motor preparation activity also varied with the transition. They approached the wide opening faster than the narrow one. EEG records voltage patterns across the scalp. It is excellent for timing and poor at locating one precise source. The study did not discover an affordance center and it did not test a city street. It supplied a more careful insight. What the body can potentially do may influence perception very early. So how could that happen? Light reflected from the street reaches rosin cones in the retina. Photopigments change shape. Biochemical cascade alters each photoreceptor's membrane voltage, and the amount of glutamate it releases changes. Retinal circuits compare contrast, timing, motion, and surrounding context. Ganglion cells then convert that process output into action potentials and send them through the optic nerve. After relay through the thalamus, recurrent activity across the visual cortex extracts edges, depth, movement, surfaces, and the larger context. The dorsal visual system and connected parietal and premotor networks continually relate visible structure to possible movements. Can I continue straight? Will I fit? Can I get across before the signal turns red? Where would my foot land? These calculations depend on shoulder width, posture, walking speed, mobility equipment, experience, and the object being carried. Several possible actions can be prepared in parallel. Continue, wait, turn, cross, retreat. Activity across frontoparietal circuits represents competing possibilities, while goals, expected effort, memory, and current body state bias the competition. Prefrontal and basal ganglia loops contribute to that bias. Cortical inputs to the striatum are mostly excitatory and use glutamate. Striatal outputs are inhibitory and use GABA. Dopamine helps change which patterns are reinforced by previous outcomes. Therefore, when one action gains enough support, motor pathways would recruit the according muscles. The movement immediately changes the evidence. A turn of the head reveals the crossing, a step forward creates optic flow. Proprioceptive and vestibular signals report how the body actually moved. Prediction and incoming sensation update each other again. Possible action shapes perception, preparation biases movement, and movement changes perception. Now enlarge the doorway into a neighborhood. The corridor is usually drawn as a line. For a moving body, it's a chain of transitions. Every curb, corner, crossing, entrance, and exposed stretch asks a small version of the doorway question. What can I do next? Consider the arterial in patches route. Along its length, it affords fast vehicle movement. Across its width, it may constrain a pedestrian. Signal timing, traffic speed, sightlines, refuge islands, curb ramps, and the position of the crossing all change to fit between body and the street. Public space works the same way. Imagine two open areas with exactly the same surface area. The first is shaped by surrounding building edges. The boundary gives the space a readable interior. The second is left between parking, setbacks, roads, and isolated buildings. Architects sometimes call the first positive space and the second negative or residual space. Add a doorway, a through path, seating, shade, or ground floor use, and the available actions change. Geometry can clarify an invitation, but not guarantee that people accept it. Light can further change the scenario. It reveals faces, edges, hazards, and destinations. Too much contrast or glare can hide information even in a brightly lit scene. And under a hot sun, visibility is only part of the problem. This gives us a better way to compare European and American neighborhoods. The tempting comparison that many people use is an old Barcelona street against a post-war Atlanta arterial, followed by a verdict about which culture designed correctly. However, large-scale analyses have found strong regional tendencies and many major exceptions. Many North American cities contain highly ordered pre-war grids, and European cities also contain coarse peripheral networks, superblocks, and car-oriented corridors. The useful comparison should therefore be morphological. How frequently does a route offer in transition? Can a pedestrian continue across safely? Do entrances meet the public realm or sit behind parking? Does open space have a legible boundary? Barcelona's perimeter blocks can create frequent corners, continuous edges, and courtyards. Selected superblock projects change which movements streets prioritize. Metropolitan Atlanta contains many branching post-war networks and large arterials, while its older grids and mixed-use districts provide counterexamples inside the same region. Neither city has one behavioral essence. Urban form changes the sequence of available actions. History, policy, climate, traffic, and land use help create that form. Now let's replay Patch's walk with a different body. Give Patch a wheelchair, a stroller, 2 grocery bags, limited vision, an injured knee, or unfamiliarity with the neighborhood. The same curb, doorway, bench, and crossing have changed Patch's affordances. Architecture therefore cannot dictate one response. It changes which responses are available, visible, comfortable, and likely to be repeated. The doorway experiment and the neighborhood do not provide the same kind of evidence. Architecture can change your behavior without giving an explicit order. By changing the next possible action, it helps us shape what the world looks like to us now.